So my name is Glenn Steeper. I'll be presenting today along with my colleague, Jon Gurnett. So firstly, I just wanted to run through some administration points that hopefully you've had a chance to read through. So firstly, just the main point is probably the Q&A button. So you'll see down the center of your screen, any questions during the presentation, please feel free to ask any question you'd like to know. If something comes up that we discuss or something that you're not quite sure about or didn't present it in a way that you have full understanding, then please post any of those questions. We have a panelist team behind us of metallurgists from Glencore Technology. So we have Adam Price, Ryan Jones, and also Matt Dunn. So those three guys will be in the background. They'll be busily answering all your questions and hopefully posting them back. If any questions are not answered during the presentation, then don't worry. We'll be basically shortly after, make sure we answer all the questions that are posted. And also, if you missed anything during the webinar, we will be posting a recording of this to everybody who's currently present, who's registered for this webinar. So you'll get a copy of this presentation so you can then have a look at it again afterwards. So on that, we'll now begin the presentation. Okay, so firstly, who are we? So Glencore Technology as a company is headquartered in Brisbane, Australia, and we've been there for 40 years. We are part of the larger Glencore group, so we sit within that larger corporation around the world. So we offer 5 technologies which we've developed on Glencore operations, and we offer these to the clients around the world. So if you see across the bottom, these are really our 5 core technologies. We have the IsaMill, which we'll be discussing today, which is our regrind technology. There's the IsaSmelt, IsaConvert, which is a smelting technology. There's the Albion process, which is an oxidative leach. And that's for refractory ores that could be base metals as well as gold ores. We have the Jameson Cell technology, which we'll also be discussing, our flotation device, and also IsaKed, which is our refinery cathode plate and also robotics part of the business. So we have a global footprint, so we execute projects all around the world. And we also have a unique access to our operations, which gives us a very good technology transfer model. And this enables us to sort of test our technologies on real world applications before we launch them. So just a picture of where we sit globally. So for most of you may be familiar with Glencore, but as you can see, we have a large spread across the world in terms of operations, as well as ports, refineries, smelters. So a large global reach. Glencore Technology. So as I mentioned before, we're based in Brisbane in Australia, and we do have a number of branches also around the world in all the major continents. So we have a good global reach within our smaller part of the business as well. Okay, so today's discussion. So as I mentioned myself, Glenn Steeper will be talking about the Jameson Cell technology. So I'll be looking firstly just at some of the fundamentals of the Jameson Cell, looking at some of the upgrade performance from the roughers that we've been seeing that have been pretty promising. I just wanted to have a quick chat about the coarse and fine particle flotation aspects of the Jameson Cell. Also look at the reduced footprint, and then some recent achievements and recent installations that we've had, as well as looking at some of the accuracy in terms of our test work and how we upscale it from the small bench scale all the way up to full scale. And we have a 1-to-1 upgrade ratio. So I wanted to just go through that quickly as well. On the IsaMill fine grinding technology, Jon Gurnett will be presenting that, and he'll be going through looking at some of the IsaMill developments and some of the overview of the operational overview. Also looking at the superior size distribution that the PSD in which the IsaMill offers. looking at some of the market overviews, some recent projects, some new designs, some footprints, some smaller changes that have been done to try and make that a smaller compact unit, and also some developments within the wear power reduction research that we're currently undergoing as well. And on the similar vein to, as I mentioned before, you'll be looking at the upscaling from a small SIG plot up to a full scale, and how we have a really good, almost perfect upscaling ability on that. He'll also be discussing a case study, which is Prominent Hill, as you can see in this photo on the side here. So we have both Jameson Cell and IsaMill installations on that plant. And at the end, I'll run through a couple of questions, see the ones that seem to be popular or the ones that seem to resonate most with people. So I will try and answer a couple of questions at the end. We'll all be running a poll as well. So it'll be a very short one, probably take about a minute to answer. Really appreciate if you could answer it. Just it's basically going to help us with our product. If we need to improve it in any way, gives us some insight into how we can actually improve going forward. So anything, if you could fill that out, that'd be great. Okay, so the Jameson Cell technology. So just a quick overview of the market. We've seen in late a lot of growth in the last 2 to 3 years within the business, which is really promising. We're hoping that, and hopefully this presentation will also resonate with you, that there's a lot of realization of the benefits that the Jameson Cell can actually add into the market. So we are seeing a lot of growth over the last few years. And if you look on the side here, you can see coal's obviously has been our biggest insulation over the years, as well as copper is obviously really big as well. But if you can see here, there's a lot of commodities that we also sell into, and we have running applications. Currently, I have over 380 installed Jameson cells, and they are growing pretty much by the month. And I suppose the key is with the Jamison cell itself is the way we sort of discuss it is, if it floats in a conventional cell, then it'll float in a Jamison cell. So it's exactly the same principle. So sometimes we get questions that say, will it work on this? Will it work on that? And the first question we come back is, well, did it work in a flotation device? Any device you've used to float, did it work? And if they say yes, and we say yes, it'll work in a Jamison cell, at least as good, usually better when we go to full scale. Okay, just some operational, the principles of how it actually runs. So for those who are not familiar, we have this downcomer unit on the side here. Now, this is really where all the magic happens. And we run a fixed pump that comes into here. We run around 150 kPa into this very high mixing zone. What this does is this plunging jet into here actually creates a vacuum, and that draws up the slurry and actually pulls it up out of the cell itself. This then draws in some air, and what it does is it pulls into this very high mixing shear zone here, where it creates very fine bubbles. And it also then has a very high contact of particles to bubbles. So this all happens in basically a few seconds. This whole thing occurs, and this is really where everything happens. So once you've made that contact, once it comes out of the bottom of the Jamison cell, out of the downcomer, then basically what we want to do is get it out of the lip as fast as we possibly can. So the whole process itself is very, very short, which is why often we say to people that residence time is not applicable. So I know some people like to think of flotation devices with long residence times. In a Jamison cell, it happens within seconds. It's very efficient in getting that contact between the bubble and the particle. And then the timing is very short, so we just want to get it out as quickly as we can. So hopefully that you can understand how there's different between this mechanism and your conventional Jameson cell technology. So we have a couple of, we actually have 3 now cell series that we have on offer. This is probably one of our most popular ones, which is the E-cell, our smaller device. This is more the rectangular shape. So the way in which it works, fresh feed comes into this feed chamber on the side, and then we have, so basically one pump is what really feeds the whole unit, which is why it's a very simple, basic unit. There's no blowers, no air blowers coming in. There's no agitators or anything. It's just simply one single downcomer feed pump, which feeds at a fixed rate and a fixed pressure directly into these downcomers, which then, as I just described before, creates the jet into the cell. So the tailings themselves, they come out of the jet, they come through here, and what we have in here is called a recycle slot, which is pretty hard to see at the bottom there. And we'll design these cells anywhere from 30 to 50% recycle. So what that means is pretty much the design of the feed coming is could be up to 150% of the fresh feed coming in. The idea of that is that basically it creates a buffer within the system. So if you look here, this is the tailings dart. So anything that doesn't report through here to come back around again reports up through this dart, which you can't see behind this arrow. And this dart here controls up and down, maintains a fixed level within this within the feed box here. Because it's a fixed pump, what it means is any disturbances that come through into the cell from upstream, whether that's come from the cyclone overflow or the regrind mill discharge, any of the disturbances, this dart valve here will actually fluctuate up and down and try and control that. So the idea here is that you always have a very stable condition within the cell. So there are no disturbances that can cause it to suddenly pulp over or anything like that. So it's a way to try and keep it nice and stable. The froth then, the concentrate is, as per normal, flows across the launder. We also have the wash water system. Here you can see these trays across the top. And this is key to maintain our really clean product. So it washes out the gang. It's very effective at getting that high upgrade, which the Jamison cells are renowned for. Okay, so now onto the B cell. So the B cell is currently our largest ones that we have on the market. However, I'll discuss a new Z cell, which we're also about to launch. And this is our larger 24 downcomer version. And we have certain ones from sort of 12 all the way up to 24. This is a round circular shape. It does have the same recycle slots, the same system as what the E-cell does. However, we have this positioned below it, so it's underneath the cell. It's not attached to the side. So that's really the main difference between those two. Okay, so what I wanted to just have a quick discussion around the bubble size. Now, this is really one of the main differentiators in terms of why the Jamison cell gets such good performance compared to your standard conventional mechanical cells as well as columns. So if you look here, basically the bubble size as you're moving your way down, so you might see 1 millimeter working your way down to sort of 0.5 millimeter. This is the rate constant, so based on a silica-based system, you can see here that it almost doubles, rate constant being pretty much your recovery in a sense. So you can see here, even with the same superficial gas velocity moving up and down, the same curve, it's really the bubble size that makes the difference, as it says there. So, and where the Jamison cell sits within that spectrum, you can see that the bubble sizes of a Jamison cell is also 0.5 millimeter. So because it has that really low, small bubble size, it gives it that superior performance where you compare it to the mechanical cells, which are up around here, and then even your columns, which have much larger bubbles up in this spectrum. So that's really the key to why it's able to get that really high recovery, particularly of a lot of fines, but also of coarse bubbles, coarse particles as well. Okay, so now moving into some of the examples of some real performance that we've been getting. And firstly, on the left-hand side, this is a large operation in Australia, a copper gold operation. And this unit in the middle here, this is our new Z8500 12 downcomer cell, which we will be hopefully launching in the next, or very shortly. And this cell here enables us to process up around 1,100 tons an hour of solid. So it's a much larger unit. It's twice as much capacity as what we see on the side here, which is our before I mentioned the B24 downcomer. So this one here is actually, yeah, twice the capacity of that. So if I just wanted to steer you towards these two graphs. Now these are, this is a Jamison cell, a demo one installed off the rougher. So this is the cyclone overflow, the primary cyclone overflow. And what it shows here in the top one here, this is where the Jamison cell results are. These little black dots down the bottom, these are tank cells. These are survey tank cells that are currently running on site. So if you look at the gold, you can see it's coming in at 0.7 grams per ton, and it's upgrading to around about 50 grams per ton at a similar recovery of maybe around 70% recovery. So that's a 70 times upgrade from the feed. Now the key here is you can see the tank cells themselves are probably going around about 10 grams per ton. So the Jamison cells getting around about 5 times the upgrade of what's coming out of these tank cells. If you look at the copper, same thing again, you've got a 0.3% head grade, and the red dot here represents the target final concentrate grade of 25%. And you can see here that the Jamison cell at around 80% recovery is achieving that concentrate grade. So if you look at that, it's around about an 80 times upgrade from the feed. Again, the tank cells are achieving around 5% in those roughers, first few roughers. And that's, again, 5 times better performance or better upgrade than the tank cells compared to the Jamison cells. So in this particular case, you can imagine all this material now can actually go directly to final concentrate. Doesn't need to go through the regrind mill, doesn't need to go through the cleaners. It enables the design then of that back end of the circuit is significantly smaller. So there's a huge amount of cost savings and complexity there that gets reduced. And obviously key to this is liberation. So liberation data enables you to get this or don't get this, because what Jamison cell does is, because of the superior washing system, it basically washes all the fines, all the entrainment, everything is taken out. So you get that really high upgrade, which is unique to the cell. On the side here, again, this is the installation we have in Russia on the rougher stream. And again, this is the real data from site, and it's 1 gram per ton feed coming in. We're achieving around 70 grams per ton, which is a 70 times upgrade. So same principles again, huge upgrade, big ability to be able to take that and send it to final concentrate and heavily reduce the size of your back end of your circuit. Just taking that information further, particularly the one on the left before I was talking the copper gold one. Just wanted to quickly point out how we sort of, in a sense, size it, and also where it sits within sort of the spectrum of the liberated versus non-liberated material. You can see here that this dotted line here is our dilution cleaning test, and this one here is the actual Jamison cell that the demo one is running on site. So on the same curve. What it does highlight is really all this material here is liberated, and all this material below here, this sort of gives you that cutoff point where you reach where it's a non-liberated material, and this is what needs to go to regrind and also to the cleaning circuit. If you look up here, this is 4 operations, rougher copper as well, and what it shows is it's quite high grade. You can see there sort of around the 30 and even 40, depending on the mineral species. You can see here that the Jamison cell all the way along here is maintaining a nice high grade as the recovery moves along. And then what you're doing here is you're now reaching towards the material, the back end, which needs further liberation. So it's very defined. The Jamison cell is very good at upgrading the material that is liberated and basically separating any gang from that stream, so you can then do something with it. And then it also gives you means that the material you have down the back is the material that needs to be reground. So it's a very good way of separating those 2 different streams. So just looking at a case, this was posted by Acadia in Australia at Mellops in 2018. And they have a Jameson Cell installation in their cleaning circuit. And this 2 columns here, one is without and one is with the Jameson Cell installed. So this is really looking at the fine particle aspect. And you can see here that in the -7 microns, this is the gold and sulfide gold, the free gold, and also the copper, so chalcopyrite and bornite. You can see the huge increase in recovery from 73 to 94, from 92 to 98, 91 to 96, and 77 to 96. A huge increase in recovery of the fines, which I think is pretty well understood with the Jamison Cell technology. But interesting enough, you look at the coarse fraction, the greater than 7 micron fraction all the way up. You can also see it's gone from 92 to 99, from 98 to 99. So it's at least performing the same, if not better, also in the coarse size fraction as well. So across here, if you look at this graph, you can see that right across the size spectrum of the particles, you can see that the gold recovery has improved over without the Jamison Cell and using the standard conventional cells that were there. And now what this is just some information around the installations we have at Mount Isa. So these are 3 Jamos that were installed in 2017. And what you can see here is even in the fine fraction for chalcopyrite, the 3 micron, you're seeing around 93% recovery, but also in the very coarse fraction. So up and around 300 microns, we're still getting around 97% recovery. So it's still very high in that upper coarse sizes as well. So the Jamison Cell has an ability to float both coarse and fine particles very effectively. So that's just a sort of maybe not a myth, but in the market there's sort of reputation as only being a fine flotation device, but the reality is actually it can do both spectrums of the size, both size spectrums, sorry. And just on the side here, this just talks about some of the rough applications that we've got either going in or currently running. And these are the sizes that they're being fed. So again, it can take and float these particle sizes very easily. Looking at a bit of a case study, just referring back to that installation of the Jameson cells in Mount Isa and looking at 3 circuits or 3 cells that were installed to replace all these cells in here. So these are all mechanical cells. You can see here that in the red squares, these are what we will replace. So the 3 columns and all these mechanical cells. And the green box at the end, this is basically the area that is what represents these 3 cells here. So huge reduction, 76% reduction in flotation surface area by installing those 3 units. And interestingly enough, they've also had a slight increase in recovery, which was already very high, but they actually had another 1% recovery that was also gained. So some really benefits, big benefits from having that included and looking at both footprint and also a little bit of performance as well. That's just an aerial view from the outside of looking in terms of what that looks like in terms of that area reduction. And just some recent achievements. So Kolawasi, we very recently just commissioned a cell in there in the cleaning application. And what I just wanted to point out here is these are the columns that were currently installed and running. And you can see this is really where the actual performance of the Jamison Cell is sitting up in this area. And these are the demo plants that were run and also the dilution testing to see it's on the same sort of grade recovery, definitely in the upper end of it. And the main key here, if you look along the bottom, this is the moly recovery. So the columns were getting around about 20% recovery, and you can see the Jamos up around almost close to the 70% mark. So huge improvement in the moly recovery. And even in the copper, you can also see it's sort of around 80 and is now up around 90%. So some really good improvements from installing that in that application. We also, you may have seen in the media, we've also sold and we're very close to placing or getting starting the fabrication of the cells for the new Britannia, which is the Hud Bay full Jamison Cell circuit. So that'll be an exciting one up in Canada. So it's a copper unit, a copper operation, and that has two roughers, a scavenger, and also a cleaner application. So it's all complete Jamison cells with no conventional cells in there at all. And these are just a list here. I won't go into too much detail, but there's just some recent installations where Again, you can see with Polyus, with Cepon, with Pogo, these are all rougher, again, rougher applications where we'll be going in and hopefully getting the same success. And the test work looks at similar success as what we mentioned in the first few slides. So now I just wanted to bring in a new concept that some of you might not be familiar with, and this is the full Jameson cell circuit. So our standard approach would be looking at obviously enabling that first Jameson cell to make a final con product. And then the second two cells would act as scavengers, which will then pull to the IsaMill for regrinding. And then from here, they would go into 3 cleaning devices. So 2 making final concentrate and 1 working as a scavenger. And so this is a sort of like a standard flow sheet, simplified, very simple flow sheet that we would recommend for certainly a number of operations. There's more complex ones which would change, but so what that relates to is this image on the side here, which I'm about to run through a model on this as well. And this sort of replicates that flow sheet. And as I mentioned earlier, these are these new Z cells that we have installed. So this is around 1,100 tons an hour of feed. The interesting thing is the size of this is 41 meters by 19 meters roughly, which is actually smaller than an Olympic swimming pool. So you have all this, including the regrind mill and all these cells and the pumps and everything with it. And in such a tiny footprint, we're able to process that many tons. So I'll bring up a model now just to quickly fly through. So, all right, so if you look here on the side, this design in particular is based on one which we're about to sell, which is why it's sort of quite high up in terms of the way it's built up. This is just an option that you can have. We also have designs where we would look at basically gravitating these lower down and then sort of basically bringing this platform right down. Having the cons potentially could be in a sump on the ground and you gravitate those in. So this is an example of one that's sort of high up on stilts, which suits the design of what we're looking at installing. However, there can be designs where it's much lower, and by gravitating, basically all these pumps are removed because there is no tails transfer that's required. The only pump you would require is this single one here, which really is a downcomer feed pump. And so one of the other things that's very interesting about this to note is, as I mentioned in the first slide, the residence time of these units is very, very short, a few seconds. So when you take into account the residence time from all the way through here, through the IsaMill, which is very short from any regrinding you need to do, and then into these cleaning devices, same again with those very short few seconds of residence time, the whole time from start to finish of this circuit is really probably only a few minutes. So if you think about startups, you think of shutdowns, you think of any sort of process control or disturbances, this whole circuit can be stabilized and can make adjustments almost instantaneous. So basically it changes the whole way in which you would run your circuit to be so much faster in terms of its response. The other thing to note with the Jamison cell is that there's only one pump. So we'll have a single pump in the center here, which can actually work as a standby for any of these 3 pumps. And the idea is really, if anything goes wrong, the only thing that can potentially go wrong is one of these downcomers may get a blockage or something. You just simply isolate that individual one, flick this off, change it out, do any changes you need to do, then basically open it back up and put it back online again. So the cell never stops. So it has a very, very high availability. You could say 99+%, because very little things can go wrong because there are no agitators, there are no blowers, nothing there that can go wrong. So that's just a quick snapshot of something that we're looking at. The IsaMill on the side here, you can see, and this is something that Jon will talk about next. This has this removable platform. So what we've done is reduce the size. This can then slide underneath, and you can bring this out when you need to do maintenance. So again, it's a heavily reduced footprint, and so it fits within this nice package here. Okay, so I will now move on to the next one. So just talking about some of the accuracy of our upscaling. So how do we go from a lab scale or demo scale or something like a pilot up to full scale? So if you're familiar with our technology, or we've done some test work on it, we've always claimed that we have a 1-to-1 scale up confidence. So a lot of the conventional ones will have 2.5 or 3 in this case in terms of how you upscale it. It's a little bit of a sort of a black art to that. Whereas with the Jamison cell, there's none of that. It's purely a 1-to-1. So whatever you get in the lab, in the bench scale, is exactly what you'll get at full scale. And we put a process guarantee of 25% cash back on that, because we're that accurate with all our last 380 installations. We know exactly where it's going to sit on that curve. And these are just some examples. You can see here the dilution cleaning test. This is graphite as example. And this little dot here, and this little dot shows exactly where the actual Jamison cell installed is running. Same here again, the dilution versus the pilot. On talc, you can see here, this is the installation here versus the test on the same grade recovery curve. Up here, the survey versus the grade recovery, the dilution test. Same on all these, the copper and then the rougher. So we have a very, very good accuracy of being able to upscale those, which gives us the confidence to actually build and design a full scale from a lab scale, bench scale test. So just lastly, this is some of our commercially available sizes of Jamison cells we have on offer. You can see here that obviously the downcomer increases to this point here, which is our largest B cell. And the difference here is the step change is the size of the downcomer. So we're now looking at going from a 280 to a 500 downcomer, which is not actually new for us. We actually have for the last 10 years been running a 500 downcomer at an operation in Canada. So it's actually not something that's new. We just really haven't moved, commercialized it formally since fairly recently. So what this does is it pretty much doubles our capacity in that, and that sort of helps us then move into some of the rougher space, but also in some of the larger applications or some of the larger projects. So thank you very much. I hope that was informative. And what I'll do now is I will hand it over to my colleague Jon, who will talk you through the IsaMills, and I'll come back on at the end just to talk through some of the comments or questions that have come through. Okay. Thank you.
I'll just get my screen up now. Hopefully, perfect. No worries. Thank you for that, Glenn. I get the pleasure to take you through the IsaMill technology for the rest of the presentation. There was a lot of feedback on the last presentation, so I thought I'd try and include a little bit more of the development history and a case study to show you how we do and deal with sites and different projects. Now, with the IsaMill, basically, what was the incentive? Why was the mill actually developed? And there was a lot of background behind this, and it basically goes back to how you deal with deposits. In the past, most coarse grain deposits are the ones that are easily exploited. And the example here I have on the left is the Broken Hill deposit. And on the right is the McArthur River. And if you had a choice between the two, obviously it's much more easy to go for the Broken Hill because you have got less energy, you have to liberate less. Now, as ore bodies change over time, the easier ones are exploited first, and we have to start dealing with the fine-grained ore bodies such as McArthur River. And it was this that kind of entered and drove some of the design of the IsaMill and how it came to be. Now, back in the 1980s, Mount Isa Mines realized that they had to achieve a 7-micron grind size for lead zinc ore bodies. This was to do with the George Fisher deposit back in Mount Isa, as well as enabling the McArthur River project to go ahead. This fine-grained mineralogy obviously required finer grind to liberate these materials. So a whole series of studies were undertaken to try and see what could be done to try and get there. And from these studies, we found that the power consumption to achieve the target was too high to try and use conventional technologies such as the ball mills, tower mills. A full study into the ball tower mills were found that it was ineffective to about 20 to 30 microns. And one of the big ones, which isn't really talked about, is the influence of the steel grinding media. When they finally tried to get close to that, they found that there was a significant impact on the flotation circuit because of all that iron that's gone into solution. So with what was out there, they realized they had to go outside the industry to try and find something. And that's where a lot of work was done and a lot of the development went. So the idea was, what other industries were out there that require fine grinding that could be adopted and changed and put into the mining industry? And a technology was found. We went out there and found that there's a company called Netch was producing horizontal bead mills. These were used in These were used outside of mining, in pharmaceuticals, paints, foods, etc. These are really small batch scale mills. What actually was tested back in the early 1980s closely resembled to a milkshake shaker, but it showed that there was enough promise that this technology could be adopted. So to try and take that across to mining, we needed to increase the scale, make it much larger, make it be able to run continuously, and make it viable by using cheap local media. And originally, the IsaMill was developed to run on sand and slag, which was an ample supply in Mount Isa. However, as ceramic medias have come on the market, we've highly recommended that you go down this route. So in the late 1980s, a lot of this work was originally developed. However, by 1994, the first IsaMill was installed, and this was the first large-scale mill, which was the M3000 at a 1.1 megawatt mill. The number behind it, the number refers to the size of the mill in litres. So our M3000 was first developed in Mount Isa in 1994, and then enabled the technology from the McArthur River Mine project to proceed in 1995. However, in 2003, we had a big project in South Africa where we were trying to try and do a scale up on the mill because they required a large volume material to be treated. However, putting 3 M3000s in wasn't cost effective. So we worked with our client. We went through the scale up process and we took it up to an M10,000 at a 3 megawatt mill. Now, the increased space allowed higher throughputs and feed sizes with F80s up to 400 microns. Now, something I want to touch on with that is that the F80 up to 400 microns is very much dependent on the media at the time. There are medias greater than that, so the IsaMill is not limited to 400 microns. There is test work out there that can push it higher. And lastly, further scale up to the M15,000, which is a 3.8 megawatt mill, which is actually, our first one was recently installed at Red Dog, and we were due to commission it this year, which I will touch on a bit later. Now, what happens in the mill? So this is a diagram, schematic of the internals of the mill. You may have seen this before, may have not. However, I'd like to slowly run through it. Slurry is pumped into the mill between 50 to 150 kPa. Inside the mill, we have a series of grinding discs attached to the shaft, rotating on a fixed speed shaft, spinning the discs at a tip speed around 20 meters per second. This creates a high intensity mixing environment. And what that does is it agitates the ceramic media that we filled into the mill with the slurry. It's this agitation that creates an attrition grinding environment that allows us to break down the coarse particles and achieve the liberation required. Now, part of the design is the high centrifugal forces end up pushing your coarser particles out to the edges and your larger media. Therefore, this allows you to keep the material in the mill and there's no bypass of the fine. So anything that will go in the mill will be ground by the mill. The finer particles, which aren't as large, will obviously pass through the middle, through the kidneys. And at the end, we have a special disc and rotor design. This, as you'll see, the gap between the last disc and that rotor is a lot shorter, and that is done by design. So by doing that, you create additional forces by that rotor rotor, and what it will do is push the coarser material out and create a back pressure down the back end of the mill. It's this that allows the internal classification and the reason why the IsaMill can be run in open circuit as we do and is our preference to design. Finer particles will then leave the mill. Now, in this example, we have 8 discs. However, what is worth mentioning is we are very keen to work with our clients, and these internal configurations can change. This can be done on trying to improve the wear parts. However, we work with them, so increasing the power, such as in South Africa. The rotor is a very efficient classifier. It reduces overgrinding and enables the open circuit operation. And lastly, the F80 is 300 to 400 microns. This is commonly treated, and we have a top size of 1 millimeter at the moment. However, I'd like to stress on that again. A lot of it is dependent on media, and right now that is from the 6mm media. However, there are different medias on the market. We have IsaMills out there using up to 8mm media currently. Now, I touched on the rotor. The rotor is really, really important because the rotor is what allows you to get a really tight, narrow distribution on your particle sizing. As part of leaching operations, you want to try and get a consistent particle. You want to try and avoid your coarse. And we look at our CSI, which is our P98 to P80 ratio. Part of the test work that went into the Albion was to look at all the different grinding technologies out there. And we wanted to achieve a good P80 grind size, but we wanted to minimize the P98. And on the bottom left-hand of the graph, you can see that a comparison study was done on a copper bulk concentrate. And the IsaMill had the smallest ratio between the P80 and P98. And most importantly, it scaled up. As you can see on the right is an example of some test work that was done back on Century. And the test work was done, and between the SMD test work and the IsaMill test work, you would look at the data and you would see that it was relatively similar. However, when it scaled up, the P98 crept up to 38 microns. This didn't scale up similar to the IsaMill on the signature plot test and is an area of concern, and I highly recommend that you look at this when investigating projects in the future, because sometimes what's done in the lab doesn't necessarily translate, and it's recommended the evidence is provided that this is the case. Now, the IsaMill market. Basically, we're all over the world. We have 130 installations spread out in a lot of different countries. Our main commodities that we're working in is copper, lead, zinc, as understandable, where the IsaMill is developed, and the platinum group metals, which is most of the South African operations with Anglo. However, we are into a variety of different aspects. We work in magnetite, gold, moly, nickel, tin, titanium, zinc, and coal. We have IsaMills producing grinds, various grind size down to about 7 microns. The top right graph shows you the size fraction that we were trying to aim for initially, but as you can see from then we've expanded, and actually most of our installations now treat material greater than 100 microns. To show you the power by commodity, as you can see, most of the power is in the platinum group metals, lead, zinc, and copper. Now, interestingly, the most popular IsaMill is the M10000, so that's the 10,000 litre variety, closely followed by the M5000. What's interesting to note is that mill is M10000 is the most popular design. However, we noticed there was a gap in the market, and we've introduced the M7500. To do that, it basically would have pulled a couple M10000s over there, but we felt there was a environment for it, and it makes it more attractive on a capital cost per power application for most new projects. Now, just to give you a bit of an update, we are constantly working and doing projects in the background, and these were some of the recent installations. Woodlawn is an interesting one, and I thought I'll go through these because it shows you sort of projects we work on, what we supply, and it's a good indicator of what we do. Woodlawn is where we supplied only the IsaMill. And this was a dual duty IsaMill, grinding from roughly 75 microns to 30, treating both tailings retreatment and a copper rough tails regrind. With that, we worked with our client. We found an optimal situation where both duties would work and felt it was a very good installation, good commissioning. The Minster B2 project was an M10,000 we installed as part of the new simplified plant supply, where we installed everything, provided the ISA control system, and we ground from 107 microns down to 74. Since this is a gravity separation tails for a tin operation, we recognize that 107 to 74 microns isn't really conventional for an IsaMill. However, it is that CSI, the P98, P80 ratio kind of drove that. There was a very strong indication that they didn't want to overgrind, therefore this drove the decision to go down this road. Hell Gold was the M10,000 as the simplified plant supply, and this was a leaching operation, gold leach, grinding from an F80 from 43 microns down to 13. This, the purpose of this IsaMill installation was to replace the 6 SMDs that they currently had running. What they were finding was they were unable to achieve the grind size, and the maintenance was becoming a bit burdensome, so they decided to go down and investigate the IsaMill option. And Actigai. Actigai was 2 M10,000s and then 100 that was supplied for a copper moly operation. Purpose of this is to show you that the IsaMill does treat copper and relatively coarse, 220 to 174 micron down to 25. They were quite impressed with how the IsaMills were operated, and as part of their stage 2, they basically ordered 2 more M10,000s and then 100. Sorry, there's a bit of water. Now, interestingly, we have a few upcoming commissionings which were interrupted due to the COVID-19 situation. The M15,000 at Red Dog. This is a quaternary grinding mill. This is a high flow mill, grind from 135 down to 65 micron. This will be the first running M15,000. Follows a lot of the scale up principles that we did with the M10,000, and really excited to see this mill up and running. And Corbin Coal, where we need to commission 2 M1000s and then 5,000, which is used to grind coal tailings down to sub 10 microns. We are really looking forward to getting these commissionings completed when we can. Now, when you see information about regrinding and stirred mills, there's a lot of misinformation with regards to the IsaMill, and I would encourage anyone that has any questions about the IsaMill to come and ask us. We'll address any inquiries you have. So I would like to say that in the presentation, and the guys in the background will be answering via the Q&A right now. We have been listening to our clients a lot, and we recognized that we had to change some designs and try and be more competitive in different regions. And by doing that, we introduced the M7500 this year, which is a 2.2 megawatt mill. And they introduced the M50,000. The flow rate's up to about 1,200 cubes with an 8 megawatt motor. This helps us to recognize what's in the environment and what people are needing. And we also changed our design to have a better footprint to work with smaller environments, small indoors, to help reduce capital costs. And lastly, with this new situation with COVID-19, we are moving to aggressively with remote support sites. So we've been able to try and get better input and help sites if they are receiving any issues with commissionings. And this is applicable to all the mineral processing technology. Now, I'd like to show you the evolution of the design of the mill. So in the top left is just the IsaMill only, and the bottom left is the original plant design. As you can see, it's large, clunky, a lot of concrete, and it's not as slick as the new design Glenn showed you earlier. We recognize that by doing that design is a little bit more expensive, and to remain competitive in the environment, we had to look at the cost. So by doing that, we went through the design, looked at what we could do, and changed it. So by doing that, we moved the media hopper to the side, Therefore, by doing this, we could lower it, so the mill now is only 1 meter off the ground instead of being 2 stories up in the air. We thought those rails were a bit long. What if we removed them? That would allow it to have a lot smaller footprint. We pushed the pump boxes back together, realized that we could tie our gland water and media charger water straight into the plant supply and move the RLSs away from being dedicated right next to the mill. And what that did was really shorten the footprint. And that by doing that, we're actually the smallest mill compared to every other competitor's design when you take into all the auxiliary services. And if on the bottom right-hand side, you'll see a mill, a vertical mill of the same power rating and in the footprint of what is required to operate the mill. And as you can see, we are one of the smaller mills. Now, we've been running and doing this test work for nearly 25 years now. And doing that, we've been doing all sorts of trials. And to do that, we've been looking at materials. We have a very good history, a very good database, and have done all these pizza flange trials, which is the picture you can see on the right. And this has allowed us to develop new rubbers within the mill, which have allowed sites to increase their power draws within the mill and improve their wear characteristics, similar to the power work we're doing in Anglo. Now, this is a lot of work, and the HD 6070 rubber has come out of that, which is the black looking rubber in the picture. We've also been doing conical spaces. Conical spaces, there was a paper published on this, and we're more than happy to share it with you, but the conical spaces are installed onto the mill, and what they've shown is they improve, there's a 22% power reduction. What happens is when media goes through the kidneys of the mill, as it heads towards the shaft, there's effectively a dead space, which takes some of the momentum of the media out. By including the conical spaces, what you do is you provide a platform that allows media to accelerate into the kidney of the next mill, conserving medium, improving your power. We have an M10,000 trial currently going on in Anglo, which is currently on hold. The initial results showed a 22% power reduction for the same grind size, and this is really promising. And I would encourage you to contact us and talk to us about these trials, because I find that you might find them really interesting and they're a really good initiative. And lastly, we have the Acoustics Emissions Analyzer. This was designed to help predict wear rates and generate particle sizings from the mill from the impact of the media on the rubber. These are really useful tools because they help prevent preventative maintenance as well as provide an alternative to the more traditional particle sizings out there. Now, how do we actually size a mill? Now, we need a few little things when we do the mill sizing, and these are throughput rates and volumetric flow. What we'd like is a specific energy requirement that is calculated from a signature plot from one of our accredited laboratories. However, if you do not have these, it's not the end of the world. We have a database that we can reference, and we can provide a power that would suit your needs. However, one of the issues behind this is we don't give the 25% guarantee on these. We do want the signature plot test work to be done. However, this is not a limiting factor of stopping a mill design. Other information we need is the application, mineralogy, and any previous grinding work. But one of the things I'd like to talk about is the data that you give us is what goes directly into mill sizing. Different applications, different design areas, people add conservative factors on conservative factors, which leads to an oversized design. We don't do that. We take what you provide, and we'll provide the mill sizing directly for that. Now, what gives us the confidence to do the guarantee? And that is the signature plot test work. We've developed a test, a grinding test. It's a pendulum style test, and the results from that test on the same conditions will scale up to the mill. We've done this on various sites such as Contour, Anglo Platinum, MRN, Area Mars, and Henry. And what we found is that when the full plant operation lies exactly on the curve. This shows effectively that we have faith in our test, and it scales up, and we're willing to back that. One thing I would encourage is people who have operations is we have the confidence in the test, I would recommend that you look at your power consumptions and what your current energy needs are and how that scaled back to the original test work, because sometimes that doesn't line up. And we have examples of that with vertical tower mills. These were done on Glencore operations and pilot sites. And what we found is a lot of people underestimate the energy requirements. They don't scale up effectively, and this was a lot of the work done on signature plot to help kind of drive this. And this is why we have a lot of faith in our signature plot. However, we're always happy to talk to you about energy. Now, I'll just finish off with the case study. It's nice and quick. One of the main ones we want to talk about is Prominent Hill. Prominent Hill is owned and operated by Oz Minerals. It's in South Australia, just north of Adelaide, and it's an iron oxide hosted copper gold deposit. At the time, this produced 79.2 million tons of ore per year, with 1.24 copper, 0.58 grams per ton gold, 3.7 grams per ton silver. Now, the client came with us and recognized there was a problem, and the problem was high fluorine within the con. What they found, every 100 parts per million of fluorine above 350 was about $1.5 as a treatment charge extra per metric ton of concentrate. This obviously makes concentrate less attractive, smelter has to treat it, and you get revenue losses from these penalties. And some environmental restrictions come in, and such as the Japanese and Korean smelters, where the concentrate levels had to be below 1,000 ppm to be able to be purchased. And initial levels were up to 3,000. So this is a problem. You can't sell your con properly. So the concentrator was a fairly conventional, aside from the high fluorine content, and a lot of work was done to produce an efficient flow sheet design to reduce it. When we looked at it, you had to realize that the gold was closely associated with copper mineralization and locked in the copper sulfide, and 80% of the gold development related directly to the copper. This is a kind of driving factor behind the design. A whole load of laboratory testing was done on drill core, mineralogical evaluation conducted, flow sheet was developed, process was verified, enough rougher con was done for regrind testing, copper con for dewatering and tailings for thickening and slurryology, as well as quantitative mineralogy. And they found that there were three options that they could go. They could go down the reverse flotation route, like Octetti, do an acid leach, or they tested regrinding and flotation down from instead of 35 microns to 20. When they did this, they found the fluorine levels decreased significantly, and there was no measurable change in the grade recovery profile. Therefore, this makes sense, regrind to 20 microns, and we found that they could use the additional cleaning capability, preferably by adding a Jameson cell as a wash froth device. So, outcomes of the test work. They found conventional grinding scheme appropriate. Flotation feed sizing was not P80, was normal 150, didn't have to change. Regrind referral concentrate to 35 ensures substantial but not complete liberation. And all the concentrates produced in test work contain a significant amount of fluorine. That was the goal, and what we found is we can address this by increasing the regrind P80 requirements down to 20-25 micron, and the IsaMill was installed for that. By doing this, there was inert grinding media, there was no detriment to flotation, and the internal classification meant there was no overgrinding, could be open circuit, and didn't have to spend additional money on cyclones as a capex cost. And the Jamison Cell was added as additional froth washing cleaning stage ahead of the conventional cleaning. This reduced the recovery of entrained fluorine and basically addressed the concern out here. We worked with our clients, we came to a resolution, and they're quite happy with the outcome. Thank you. We're more than happy to answer any questions. I will start a quick poll and give control back to Glenn. Thank you.
Thanks for that, Jon. So as Jon just mentioned, and I mentioned at the start, we have a poll that would be really appreciative if you could just answer some questions on that. It's very short, multi-choice questions, Should only take about a minute. It's just great for us for feedback in terms of what the market thinks of our technologies and where we can improve going forward. And just a couple of questions I mentioned I was going to answer. So I have two that I've picked that I think seem to be a common theme. One was from Chris Garrido, and he asked in regards to the coarse flotation of copper in terms of what is the size in which the Jameson cell can float to. So I'll just quickly jump, sorry, move that off the screen. I will just quickly jump to the slide that's appropriate to that. I think this question may have come in before I actually went to the slide, so hopefully he might already be aware of the answer, but I'll just go over it anyway. So basically what this slide here just talks about the chalcopyrite, which is obviously the copper application, and just talks about the size spectrum in which the Jamison cell can float to. So up here you can see it's getting up around sort of 300 microns at 97% recovery. And if you look at the 200 micron range, it's right up around the 98 to 99% recovery mark. So in terms of the coarse size fraction, that the Jamison cell can go right up into that high level. And what we see is, as I mentioned, that the typical bench scale test application, which is your Denver, for example, whatever that unit can float, because it has also a high shear and high bubbles, whatever that can float in there, the Jamison cell can do exactly the same. So it can go up to quite a coarse. There aren't that many applications where you would see a rougher feed of over sort of 300 microns, but the Jamison cell can float effectively up to that size in terms of the coarseness of the product. So I hope that sort of just covers that off. The second question came from Lyle Tritton, and he was asking basically some questions around the test work sample and also just some of the options that we offer for test work itself. So on that, we do have sort of three applications where we work within. And the first one is a dilution cleaning test. So this procedure, which we will also send out at the conclusion of this to everybody on this webinar, that can be done in any single lab, anywhere in the world, really, any competent lab that has something like a Denver or some sort of similar device. Now, the idea of that is probably 2 to 3 kilograms. We take that material into the cell. We do 3 stages of cleaning. So what it does is it replicates the very high washing ability, froth washing ability of the Jamison cell to get that very high upgrade factor, which is what I talked about at the start. I talked about how it's able to get that sort of 70 to 80 times upgrade. And by doing that, what it does is having that dilution cleaning test, it basically simulates exactly that. So that will produce a nice grade recovery curve from basically all the way from the start, all the way down to the bottom. And that information there we can use to size the different cells required to achieve whatever duty it's required to get there. What we then have is we have the couple of sort of demo lab pilot scale equipment. And I'll just bring up an image of the first one. So this one here is the L150. So this unit here, we can run, basically, we have it in a number of labs around the world, and they're also portable, and we can send them to any sites or any labs as well. Now, what this unit can do is we can run a batch. This is sort of minimum around 20 kilograms, and what we'll do is we'll actually batch it through this unit, and that will give us, again, a very nice profile of grade recovery, what you can expect from all the way down in the Jamison cell. The beauty of running it through this is that it does give us a very good understanding of the froth wash as well in some of these applications. So, sorry, on this as well, if we want to run continuous, in other words, if we want to actually run a continuous feed all the way through and not recirculate back through the tailings, then what we need is around about sort of 100 kilograms of material. And if we want to now look at the larger unit, so this is our L500 unit. So this is a much larger unit, approximately around about almost 4 meters in height. And this is the one that we send to site. So this is not really based for a laboratory scale, unless it was a very big demonstration plant. So we typically send these to sites, and we send them all around the world. And you basically plug it into a stream, a bleed stream that comes off wherever you want to run this off. So it could be the cyclone overflow. We have a little bleed stream that comes off there. It could be the regrind discharge. It could be wherever you want to test this material. So, and this roughly is can take around 2 up to 15 meters cubed per hour. So that's the feed rate that comes through. So, and as you saw, all these tests, whether it's the lab scale, whether it's the L150 or our larger L500, any one of these can be scaled directly from 1-to-1 to full scale. So what you get in these tests is exactly what you can expect at full scale. And so we have this, for instance, the L150, sorry, the L500. We have a couple of units in the Americas as well, based over there. So we can move those around to various sites as required. And same with the L150, we have some laboratories in the Americas as well, where we have these things set up with various labs that we can steer you towards that can help you run these if you wanted to get some more information. But the dilution cleaning test that can be done, could be done on a site laboratory on any place. It could be done in any laboratory that has a functional lab scale test rig. You just need to make sure you follow the procedure, which is not too complicated. Just need to follow the procedure, send the information to us, and then we can easily interpret that and come back to you. The other thing to note is we do have an online calculator, which is not, we have an old version at the moment. We are refreshing it with a new version, hopefully in the near future. But in the interim, you can feed some information into there, and that'll sort of help size the equipment as well. So I hope that answers those questions. And I hope you've all had a chance to also complete the poll, which would be really appreciative. And that's pretty much the conclusion of today's webinar. So I hope you've all enjoyed it and found it very informative. And yeah, good evening to everyone, or afternoon.
Thank you.